Hello.
Hi, I wasn't here Tuesday.
That's fine. You're Ariana, right?
Yes.
Well, this is kind of an extra, so I'm going to start 2 minutes early. And I think maybe the people who come in now will get scared. We'll try and show up early. So Tuesday, we came across, I put this problem that was from the book. And I showed how you find the square root of 2 over 3. And then someone said, well, the book, negative infinity. And I forget exactly what this looks like, but it, function did something funny around 0 and then went here and here. And whatever the strategy I used to solve this, if you very blindly followed it here, you got positive square root of 2 over 3. And someone pointed this out, and I looked at it, and I was scratching my head. I'm not very smart when I'm in front of the blackboard. But I went home, and I found out it's kind of a... once you see it, it's very simple, the kind of thing that could mess you up. So the first thing I'm going to do, to give you an idea what the problem is just write an equation. I'm going to write 2 equations. Okay, so now what is the solution to this? Take a look at what's x? What's the solution to that? Anybody? There's a small trick here, but it's very small. Anyone? All the unshy people are not here yet, so I'll solution set is square root of 5 and negative square root of 5. Second degree equation has 2 solutions. This is a linear equation. It just has 1 solution. And therein lies the whole kind of crux of this problem. We have this symbol which doesn't mean this exactly. It means the positive square root. So, if I made the provision that, x greater than or equal to 0, then and they're both the same. So that's kind of what we have over here. We've got a square root of x squared, and the book points it out in a little different way. So you might want to notice that square root of x, negative square root of x squared is x, right? So negative square root of x is square root of x. Here's another thing you can look at. If I say, is this true? Is that a true equation? Is that correct? Well, no, not really. It's not true for all real numbers. It's only true if x is greater than or equal to 0. like if I plug in -3, if -3 equals 3, which of course is true. So that's what happens here with this going to negative infinity. So how would you go about actually solving it and getting the right answer? Well, what I did before is I multiplied by 1 over x over 1 over x. That's fine. But when I divide this square root of 2x squared plus 1 by x, well, really what I'm doing is, the mistake is if I put this in there. Because x is less than 0, this is a positive value, it's wrong. It should be like this. And then we just get 3 minus 5 over x. So that's kind of the tricky part here. This is where the minus sign comes from, in the fact that you have to look at the x's, they're all negative, and so that's what we have here. I got that right. All right, that was, I said I would follow up on this. I put this up on my website if you know where to find the notes. Just a little song and dance explaining it.
Example 4. Example 4.
It's example 4? Okay, I didn't jot that down. It's tricky enough, it's algebra. It's not calculus, it's algebra. And I'm not I wouldn't fret over it. It's not gonna throw you off too far. Okay, let's see. So first, I'm just naming people who aren't here. Maya, Natalie's not here. Alexis, you are? No. Alexis? No, Alexis is not here either. Maria's here, right? And Rossi, Efon's here. Are you Yavi? You're Egypt. This is your seats. You want to change? So you're sitting in Danny's seats, who's not here. How do we want to do this? Do you guys want to move back to the seat you picked, or do you want to stay there? It matters to me. You have to choose. You don't have to. You just have to tell me what you're going to do.
Wait, where did he sit before?
He sat over here.
Okay, well, I sit there.
Okay. All right. So you two are going to switch. All right. You wanted to be in the front row anyway. That's where all the smart students are. That's where all the A grades are, right? Okay, so Yavi and Danny aren't here. Emily, Montserrat, Lisa. I think there's an epidemic going on here. I think it's named after a Greek letter. Okay, before we get going again, any homework questions that are still floating around? I feel like apologizing, but my grader has been a little slow getting started. I'm pretty sure the first papers will come back on like Tuesday. There will be a third assignment which I'll post today based on what we do. And that's it. Okay. All right. Yeah, I have a nice new eraser now. Came in. Nobody can figure out what this side is for. Feels nice on your hand. Oh, yeah, that's what it's for. Okay, so getting back to where we left off, we have this idea that we have a continuous function, and we have some x, and the value in x, and we have some other point a little off, x plus h, so the distance is h. And we have an approximation of a tangent to the curve at x as this line through these 2 points, which gives us this formula. Well, I'll leave that formula out for a moment. F of x plus h minus f of x over h. This formula is the equivalent of delta y over delta x, the slope of a line. And now we make this calculus. We take the limit as h approaches 0. So we're taking this line, this point, and we're bringing it closer and closer. The closer we get to a tangent at that point. And we take the limit, we call, the value of that, the slope at that point. And since I've done this generally for x, we call this the derivative of the function of x. This is one form of notation. It sort of comes from Newton. We credit, well, there are lots of mathematicians involved with the development of calculus. We credit Newton, an Englishman, and Leibniz, a Frenchman, for developing it. They kind of developed it around the same time. Actually, Newton, his notation was just to put a dot over it. And you might see that in some books. But generally speaking, we use thank you, apostrophe. The equivalent Leibniz notation, you'll see something like df dx, or e dx, f of x, or sometimes, we'll say dy dx. Talk about y equals the function. And this kind of looks like a ratio. Kind of looks like a fraction, but it's notation. You shouldn't treat it as anything else. There's a section later in the book where they'll talk about something called an infinitesimal, d of x being an infinitesimal. I don't think that's useful at this stage of the game. It's kind of arcane view of this for beginning math students, calculus students. Okay, so here we have, mark this down. You kind of want to know this. You want to recognize it both in its current form and when we actually insert a function here. There was a homework problem with the limits that actually used this form. It was kind of a trick to get you to do a derivative before you knew what a derivative was. All right, so let's try and use this definition. So I'll even write this here. Definition of a derivative. I guess it might help to also say a derivative is a function, just like our function. All right, let's try an example of this. Let's say our function is good old vanilla parabola, x squared. So our definition says that the derivative of this function, the limit as h approaches 0 of f of x plus h, which is x plus h squared minus f of x, which is x squared over h. All right, so now we just need to evaluate our limit. Well, we do a little algebra here. We get x squared plus 2xh plus h squared minus x squared over h. And the x squareds cancel. And we can take out a factor of h here. So we end up with what? 2x plus h, this limit. And we use our limit laws. Says that the limit of a product is the product of a limit. So we know the limit of h over h is just 1. And we know that the limit of this polynomial, 2x plus h, as h goes to 0, is just 2x. So we can say that this is 2x. So we have a polynomial parabola. And this is our f of x. And down here, our derivative kind of looks like this. It's a straight line with slope 2. All right, let's think about this for a second. What does this say? Down here at 0, it's 0. The tangent of this parabola at 0 is 0. As we move up here, like if we go to 1, then we have a slope here of 2. We go down, back over here, now we have a slope of minus 2. And as you see, as we get larger and larger, the slopes get larger and larger. You want to start, when you look at functions and their derivatives, you want to start thinking of it that way. That, again, this describes the slope of the tangent at some point. Right? And this formula gives us a way to find that function, the derivative. All right. Let's do a real, I hope everyone has this down. We're going to do a really easy one. I think we might have even done this before. Or we might have talked about it. All right. We're going to take the derivative of a line. Or the definition says it's the limit as h approaches 0 of f of x plus h, which is m times x plus h plus b, minus f of x, which is mx plus b, all over h. All right, again, we'll do a little algebra. We have mx plus mh plus b minus mx minus b over h. Mx's cancel, b's cancel, and we just have an h, mh over h, which is just m times h over h. Using our limit laws, we see that this is just m. Well, this should not be a surprise. We have some line, goes through b, and it has a slope delta y over delta x equals m. But if we try and form a tangent at any point, it's just the line itself. So the slope is just going to be, itself is going to be a constant function at m. So that's the super easy version of using this formula. All right. Any questions so far, yes, George?
I think I seem to recognize the x plus h squared minus x squared over h from somewhere. I think it's because of variable.
There was a problem either with x squared or x cubed in the homework for limits.
I think it was like part of pre-calculus. I'm not sure. Just that equation.
Couldn't make out. Sorry.
That's right.
All right. Okay. All right. Let's do something a little more interesting, a little more challenging. I mean, it'd be nice if finding our derivatives was always this easy. Won't be, but we're going to develop some tools that can make it pretty easy. So instead of x squared, let's get square root of x. So we want the limit of x plus h minus square root of x over h. That's not so obvious how we solve this, but we've been working with, sorry, I just want to take a scan. We've been doing things like this, and there's this strategy that, sometimes works. It's the a squared minus b squared strategy. Let's multiply this by square root of x plus h plus square root of x. And of course, we have to make the numerator and the denominator the same, so it's just in the form of 1. And what do we get? We get x plus h, square root of x plus h squared, which is x plus h minus x square root of x squared, which is x. And on the bottom we have h square root of x plus h plus square root of x. Again, with the limit. All right, the x's cancel. And we're back here with what? We've got h over h again on 1 over square root of x plus h plus square root of x. And this is going to go to 1. h here is going to 0, so this just becomes 1 over 2 square root of x. So that's our derivative of the square root of x function. All right, there's one more example in my notes. I'm not going to do it. It's just, I don't think there's much to learn from it. If you're interested, it has to do with the problem we already did. We already did it, I think, in the first class, and we did it without calculus. We looked at a circle, or at least the top part of the circle, and we used just geometry to find the slope of the point. And you can do that. You could use the formula. If you want to check my notes, see how it's done. It's an exercise, is what it is. So, and you come out with the same result, or you should. All right. So now I want to talk about something. I want to discuss differentiability versus continuity. So we have a definition of continuity of a function where the limit as x approaches a of f of x equals f of a, we have a continuous function. And continuity is a requirement for differentiability. If the function isn't continuous at a point, you're certainly not going to be able to find the derivative. You're not going to be able to, I'll write the definition. You're not going to be able to find the derivative. On the other hand, if a function is continuous, is it always differentiable? It's kind of a reasonable question. So to investigate that, we're going to look at this function. F of x equals absolute value of x. And it looks like this. Now, it's easy to see that when you're not at 0, you just have straight lines. So it is going to be differentiable there. So the interesting question is, what about at 0? So if I take this limit, take x plus h minus x over h, and I want to know the limit as x approaches, as h approaches 0, what happens? Well, this is just the slope here, right? Which is just the slope of the line. So coming from the right, you have a right-hand limit. Which is just going to be 1. But coming from the left, it's going to be minus 1. So the limit you need to find a derivative does not exist. So even though the function is continuous at 0, it's not differentiable. Now, what can we learn about this? Well, you can have a function whose derivative changes direction. And it will be, whose value changes direction, whose slope changes direction. It will be differentiable, but it has to be smooth. You have kind of points like this, like you have at the absolute value function, at these points where the function kind of changes direction drastically, it will not be differentiable. You won't have a derivative defined there. So that's something else to keep in mind about derivatives. All right. So let's kind of summarize here. So to be differentiable, function must be continuous. That's a requirement, but it's not adequate. This limit has to exist for it to be differentiable. Question then is, if the function is differentiable, we say at a point, is it continuous? And we're going to find that that's the case. I'm going to do kind of a formal proof here. Ask questions if there's anything unclear, but don't feel like this is going to be something you'll be asked to regurgitate on an exam. This is something, if you take an analysis class, we expect from you. Okay, so the first thing we're going to do is we're going to prove a lemma. Has anyone not heard this term before? Anyone want to know what? Okay. We're going to prove a theorem. If a function is differentiable at a point, it is continuous. That's a theorem. A lemma is a theorem, but you can think of it like a little theorem that we use when we're solving a proof. Gives us a little stepping stone. So, all right, so we're going to start. I'm not going to give away what we're proving yet, but if f of x is continuous, then by definition, the limit as x approaches a of f of x equals f of a. That's our definition. So we're going to let x equals a plus h. So how's that going to change this? Well, that means our limit as a plus h approaches a, f of a plus h is going to equal f of a. I've just substituted for x in this equation a plus h. Now, when we talk about the limit of a plus h approaching a, what we're really saying, of course, is the limit as h approaches 0. So what we're saying is that f of a plus the limit as h approaches 0 of f of a plus h equals f of a. Well, this is true for all a. I didn't specify a. So I can just replace a here with s. And I can say that the limit as h approaches 0 of f of x plus h equals f of x. Okay, that's my lemma. This is what I wanted to show. In retrospect, it seems kind of obvious, but it's actually only true because f of x is continuous. That was the requirement. All right, so now we have our lemma. It'll come in handy here. Okay. So, recall what we're trying to prove is that if a function is differentiable at a point, it's continuous. So, we start with the idea that, well, what if h is not equal to 0? Then f of x plus h minus f of x is also equal to f of x plus h minus f of x divided by h times h. Just think about that. H is just, it's not 0, so I can divide by it and multiply by it and get what I started with. All right, let me find the limit on both sides here. Okay, so this right here, that's my definition of derivative. So we have that this is just equal to derivative times h. Let me say that right. This is the limit as h approaches 0 of derivative of x times h. But clearly, this is 0. H goes to 0, so this is going to be 0. So we have that the limit as h approaches 0, f of x plus h minus f of x is 0. Well, the limit of f of x as h approaches 0 is just f of x. So we have that the limit as h approaches 0 of f of x plus h is equal to f of x. But by our lemma, if f is continuous, excuse me, by our lemma, f is continuous if this is the case, which is what we just found here. I don't know how this is coming across. The takeaway here is if a function is differentiable That's what you have to retain for this. Okay, any questions about this right now? We're gonna do some useful stuff in the second part of the class. I think I'm gonna pause now, take a break. Yes? I'm sorry, can I? Oh, okay, okay. So this statement here is true because I've said h, not 0. Right? I can then take the limit as h goes to 0 of both sides. Right? On this side, this particular piece is the derivative. Right? So I've got the limit as h approaches 0, the derivative times h. But this is right, the limit as h approaches 0 of h is 0. So the product of these two is 0. So my conclusion is that this limit here on this side is equal to 0, but f of x doesn't depend on h. So I can say that this limit goes to f of x. I think I know what's confusing about this is I'm starting with the assumption that f of x is differentiable. That comes in right here. If this isn't true, then the proof falls apart. It's because we know the function is differentiable that we can make this statement that it becomes 0, and that gives us this statement, which is equivalent to the function is continuous. Is that how it goes? This is math. This is kind of abstract math. Again, don't panic if it's not obvious how this is working. All you need to take away is that if I have a differentiable function, I know immediately it's continuous. If it's differentiable at a point, it's continuous at that point. Okay? All right, like I say, we're going to take a break now for a few minutes, and we'll come back and we'll do something a little more down to earth and a little more practical. 3.1 in the book, derivative formulas. Spelling here. The skill to do this is going to consist of two things. One is we're going to have a list of well-known derivatives that we know. And we're going to have some tools or formulas or strategies that are going to allow us to combine them. So we're going to start learning some of these formulas or strategies here. Let's first start with a short list here of functions and their derivatives. You already know. So we have f of x equals some constant, and the derivative is just 0. I think that should be pretty obvious. You have straight line constant, its slope is always 0. We saw that we have a line that our derivative is just m, the slope of the line. And we, using our formula for a derivative for x squared, we came up with derivative 2x. We saw that derivative of the square root of x is, I must have made a mistake when I was deriving it, and somebody taught me. Negative. Oh no, I think this is my error. I'm sorry. Went over 2 squared. I did do it. All right. I have a bug in my notes like this. And we also found out for the upper half of the circle that the derivative slope at each point on the circle, this we actually did in the first, I think in the first class, or the first or second class, 1 negative x over square root of 1 minus x squared. It would be very tedious to keep having to use that formula with the limit. So we want some better way, to be able to combine these things that we already know. The first such formula is the sum formula. It says that the derivative of the sum of two functions is the sum of their derivatives. Right. We'd like to show that that's the case. So let's use our derivative formula. F plus g prime of x is the limit. This is a real easy limit proof, so don't panic. F plus g of x plus h minus f plus g of x over h. Well, this is easy to compute. This is f of x plus h plus g of x plus h minus f of x minus g of x all over h. Now we can recombine this. Well, now it's starting to look like what we want. We can use our limit laws. It says the sum of a limit is the limit of the sum. We can break this up into the limit as h approaches 0, f of x plus h minus f of x over h plus the limit as h approaches 0 of g of x plus h minus g of x over h. But here we just have the definition of the limit of these two functions. This is just f prime of x plus g prime of x. So that's our sum formula here. How could we use that? Well, we have some function f of x equals x squared plus 3x plus 4. You can see we've got two functions here that we're familiar with. The derivative is just going to be the derivative of x squared, that's 2x, plus the derivative of 3x plus 4, that's a line, that's 3. So that's how you can use this formula. Whenever you have a sum you want to find the derivative of, you can find the derivative separately of each term. Right? I'll let that settle in for a minute. Okay. Similar function is we want to find the derivative of some constant times a function, and that's just going to be the constant times the derivative of the function. Once again, the proof here is pretty straightforward. K of f prime of x is going to be limit as h approaches 0 of k f of x plus h minus k f of x over h. But recalling that, well, we could break this up into, well, it doesn't matter really. We recall that the limit of a constant times a function is just the limit, just the constant times the limit of the function. So this is just k times the limit h approaches 0 of x plus h minus f of x over h. And that, of course, is just k times our derivative. So all that writing just to mean constants can move in and out. If I know some derivative, I can multiply it by any number I want. I can multiply the function by any number I want, and that just multiplies the derivative by that number. Right. Okay, now, next is one of the most useful formulas. You've got times a constant, a sum. It'd be nice to know what the derivative of the product of the two functions is. And this is where wishful thinking doesn't get us where we want to go. It would be really nice if this was just the derivative of f of x times g of x, derivative of g of x, right? But it's not. So don't write that down and don't remember that. Instead, at least it's kind of symmetric. It's f of x times the derivative of g of x plus g of x times the derivative of f of x. And since addition is commutative, you can write it either way. And multiplication is commutative, you can write these either way. All right, well, let's see how we can show that. So, f times g of x, the derivative of it is the limit h approaches 0 of f times g of x plus h minus f times g of x over h. this point, we metaphorically, I guess I'm a magician up here, I metaphorically pull a rabbit out of my hat. And what I do is, in the numerator here, I add f of x plus h times g of x, and I subtract f of x plus h times g of x. I can do that because it's 0, right? Doesn't really change anything. Well, I guess I'm gonna have to rewrite this a little here before I move forward. This is f times g of x plus 8 is f of x plus h times g of x plus h. That's just notation. Minus f of x times g of x plus f of x plus h times g of x minus f of x plus h times g of x. Right, so I have two terms here that are f of x plus h, so I'm going to factor that out. So that's g of x plus h. Guess I'm going to take this factor minus g of x. And then what do I have left? I have f of x plus h times g of x minus f of x g of x. I guess I really wanted to write this factoring out g of x here, right? Okay. Starting to come into focus. I have f of x plus h times g of x plus h minus g of x over h. Plus g of x times f of x plus h minus f of x over h. Well, this limit here is just the derivative of g. And this is just going to go to f of x. This is g, and this is just the derivative of f of x. So we end up with f of x, g prime of x, plus g of x, f prime of x. So that's our formula. That's how we derive it. Let's try and do something. Is everybody done with this? fun to go through, but again, you're not going to have to put this on an exam. This is just this is how we get there. Wait a minute. Done? See, Eleanor's busy. You can find this online in my notes too. Okay, so now we're going to do something I think is fun. But that's just kind of a math professor. Does anyone, I guess I'm going to ask this in the negative. Does anyone here remember what a proof by induction is? Proof by induction. Okay, they left that out of your preparation. That's okay. It's real straightforward. We've seen a few functions here that involve just an x. Right? Here's like x to the 0. That's a constant. We have x to the 1, x to the 2. We're going to come up with a formula for the derivative of x to the n, which is going to be n to the n minus 1. This is called the power rule. This is the product rule. Sum rule. Call this the constant rule, I guess. We have a few examples here. And we'd like to show that this is true for all integer n. And there's a pretty standard mathematical way to do this. If you have a series of propositions, theorems, well, we'll start with 1, 2, 3, and you want to prove all of them. Just all at once. So the way you go about this is you first prove what we call the anchor. You prove P of 1, proposition 1. Then you show that, if proposition n is true, then proposition n plus 1 follows from that. All right, so you got to follow the logic here. We proved 1, and we proved if n, then n plus 1 is true. We proved 1, then 1 implies 2, and 2 implies 3, and 3 implies 4. So you've got them all. It's kind of cool. It's kind of cheating. You don't have to do a lot of work. Okay, so let's see if we can do that. Well, we already showed that the derivative of x, right, f of x is x. The derivative of x is just 1. Now, let's see here. Derivative of x1 is 1 times x to the 0 is 1. Oh, okay. So we got our anchor. Now what we want to know is, assume that f of x equals x to the n, that f prime of x equals x to the nx to the n minus 1. Assuming that, we want to show that if f of x equals x to the n plus 1, that f prime of x is going to equal n plus 1 x to the n. All right, so assume this, prove this. Okay. Well, thank goodness we have our product rule. Okay. So what we're going to do is we're going to find the derivative of x to the n times x. Right? That's x to the n plus 1. So let's find the derivative of this. All right? The derivative of x to the n times x is the derivative of x to the n times x plus x to the n times the derivative of x. I did that really fast. Remember, derivative of the product is of f and g is f times the derivative of g plus g times the derivative of f. So my product is x to the n times x. So it's the derivative of x to the n times x plus x to the n times the derivative of x. All right. But we know the derivative of x to the n. That's n x to the n minus 1. That's part of our assumption. And we're going to multiply that by x. And we know the derivative of x is 1. Okay. So n to the x, n times x to the n minus 1 times x, that's n x to the n plus x to the n. And we're going to factor in the reverse way, is n plus 1 times x to the n. That's just what I wanted to show. Okay, this derivative is this. So now I've proved it for all integers greater than 1. You know, I just noticed something. I can just notice this. Kidding. Can I erase this? Okay. You always see the power rule written this way with n. Okay? But look at derivative of the square root of x. That's really the derivative of x to the 1 half. If I apply the power rule here, what do I get? I get 1/2 x to the 1/2 minus 1, negative 1/2. It's 1 over 2 square root of x. That's exactly what we found the hard way. So it kind of looks like the power rule works for more than just integers, for more than just, I guess, natural numbers. And in fact, that's the case. It works for integers. That, you know, of course, includes negative numbers, fractions, and, rationals. It actually works for all real numbers. Derivative of x to the pi is equal to pi x to the pi minus 1. It works for any number. We're not going to prove that here. Just now you have that in your toolbox. So I'm going to use this board a lot. So I want to leave these rules up for now. You know, I guess often I say, well, you don't really need to know this. Everything on this board you really need to know. So you take it in your heart, you're going to do homework problems on it. Something, we're going to have one of these formulas that I haven't put up yet. It's a little more confusing. I didn't have to think about it every time. Just do it that way. So write it on that, piece of paper I let you take to your exam. You get a sheet of paper with some formulas. Okay, let's just do some simple problems. What if f of x equals 12x cubed minus 6x minus 2? What is f prime of x? Well, according to the sum rule, I can take this term by term. And these are just, monomials. This is a polynomial, so the terms are monomials. So the derivative of x cubed, is going to be 3x squared. I got a 12 here, that just multiplies it. So it's 36x squared. I only did a sum rule, but we're adding a negative, right? Same thing. Derivative of 6x, well, the derivative of x is 1 times 6 is 6. And the derivative of minus 2, that's 0. So polynomials, you can just rattle them off like that. Really easy. Let's try one more for good measure. We'll call this p of x.
That is just minus 6 though, right? That is just minus 6, right?
I'm only hearing half. Something is minus x?
No, it's just minus 6, right?
Yeah, oh, I'm sorry. I didn't mean to confuse. Plus negative 6.
No, I was like, I was just wondering why it was.
I was, because I didn't put a minus here. I guess I did plus or minus. 1/4 x to the 4th minus 2x squared plus x plus 5. So the derivative, again, just really easy. You take the exponent, multiply it by the coefficient if there is one. 4 times a 4th is just 1, and you subtract 1 from the exponent. Multiply the exponent times the coefficient, and subtract 1. This is just 1 and this is 0, so we're done. So finding the derivatives of polynomials is really easy. Let's see. Ran out of room. Okay. Turns out get this going here. Well, so, moving along is now going to be section 3.1. Exponential functions. So we have the function 10 to the x. And we want to know the derivative of that. Recall that exponential function kind of looks like this. It's going to go through 0. It's going to go through 1 at 0. And we're going to go back to our formula. Right? What can we do with that? Well, we can take out a factor of 10 to the x here. Okay? This is 10 to the x times 10 to the h. It's 10 to the x over h. So and since there's no h here, we can move it outside. So again, the derivative is going to be 10 to the x times the limit. That is 10 to the h times 1 over h as h approaches 0. Something down here that I don't understand yet, so I can't really explain it until I understand it. Oh, I see that prime is 0. I guess this is pretty easy, right? F of x is 10 to the x, and the derivative is just 10 to the x times, it looks like some kind of constant here. So we just have to get a handle on what that constant is. We're going to, so I'll have to turn off the lights. We're going to make use of our friend Desmos. Can everyone see the screen out there? I can barely make out. waiting for something here. Oh, here we go. LED brightness. Yeah, this monitor up here is at full brightness and I can barely see it. All right, well, see if we can't make it do anything. Okay. So, anyone here who's not familiar with Desmos, desmos.com, a wonderful tool for learning math.
You have to pay for it, or is it free?
I'm sorry?
He asked if it was, you have to pay for it, but you don't have to pay for it.
No, it's free. Okay, so I'm curious about 10 to the h minus 1 over h as the limit goes to 0. So I don't know what Desmos would do if I gave it an h, but so here's 10 to the x minus 1 over x. So that's the function. And I'm interested in what happens as I get close to 0. To something between, I don't know where this can hit, somewhere between 2 and 2.5. We'll just, whatever this constant is here, between 2 and 2.5. That's all we know right now. And well, maybe I can actually get over there. It's undefined. Oh, 2.276. 2.25. Yeah, I mean it's around there. Okay. Well, let's make believe instead of 10 to the x, I was looking at, say, 3 to the x. Okay, so now the constant is a little lower, 1.057. Let's try 2. So, marker. There it is. Just want to have a little chart here. So, assuming I'm looking at a to the x, and that constant said for 10, it's about 2.2. 3, it's about 1.105. 2 is about 0.708. Just doing a little numerical investigation here. It looks like somewhere between 2 and 3, that constant would be 1. Anybody seen this before? So I'm looking for 1. See, there's some function where the derivative, equal to a to the x, where the derivative is just going to equal 1 times a to the x. And I want to know what a is. Well, it turns out this is 2.718281828, and then a lot more numbers. So someone who's seen this before, remind me where you've seen it before. This is Euler's constant. E, yeah. All right, that was a whole big, long, crazy thing. Yeah. So, f of x is e to the x, and f prime of x is e to the x. Kind of swooped in on that. Where have we seen e before? Anybody remember? Somebody remembers. If you remember the number. So maybe in algebra or pre-calc, you were doing an interest calculation. So you have some investment at some kind of interest rate. You calculate a future value is the present value times 1 plus the interest times time, whatever that is. Your interest is in yearly, and this is in years, monthly, months. I guess we should interest year, months, forth, days, minutes, seconds. So as you start using smaller and smaller increments, you make a little more money, but at some point it kind of levels off. It doesn't become infinite.
You doing annuities?
Hmm?
We're doing like annuities and.
Yeah, it's like an annuity. Annuity involves interest. So we have this idea that we have continuous interest. It's kind of like you hand the bank your money, you start your stopwatch. starts clicking, and then you stop it and you say, give me back what you owe me. And they have to give you, you know, up to the instant, right? Well, nobody does that, but we can calculate it. And the formula is future value equals present value times e to the, I think it's IY, interest times the time involved. So that's usually where people first see E. It's this, you know, like pi is approximately 1.9. E Euler's constant. It's probably the second most important number in mathematics. Shows up in lots of places, but you know, it shows up in interest. It just showed up in calculus. It's the only value, the only exponent, it's only the only constant where if you find the derivative of the exponential function, you get the same function back. This has enormous applicabilities. If any of you guys are interested in science, biology, physics, and economics, you run across differential equations. And this function is just extremely important in solving differential equations. You can kind of see why, because if you have an equation like, you know, y equals some constant times the derivative of y, like, oh, what's that going to be? Well, looks like this is a good choice, a good place to start looking. Okay. I think that's yeah, I just had okay, so keep this, you know, burn this chart into your head. I wouldn't worry about this. We'll figure out how to, you know, this is power rule. Power rule, exponential. You know, you want to know all these. This is going to come in really handy. I do want to just want to spend just another minute or two on notation. Say I have some function just leave it at that. I find the derivative. Well, I might want to find the derivative of the derivative. Okay. How would I write that? Well, one way is I could put 2 marks here. That would be what we would call the second derivative. I could do that again one more time, maybe. I wanted the third derivative. But anymore, and it kind of gets cumbersome. So the notational way of dealing with this is put a Roman numeral up here, so 0. So this is the Newtonian way of writing this. Now, if instead we were going to use Leibniz notation, the way we would write the second derivative is we would say e squared x squared f of x, and so forth. 3, third derivative, fourth derivative. It's just notation, and it just means you have a function, you take the derivative, then you take it again, again, again. So that's the notation. If sometimes in 5 minutes we'll talk about a function y equals dy dx. And again, we're going to write it d squared y dx squared and so forth. It's notation. It doesn't mean something. These aren't exponents. Just look at it as notation. So, okay, thank you. As I said, I will post later today. Assignment, see if we can get it done by Tuesday. But again, emphasis is always on